but now it works. Okay, so last time we uh, stopped at a place where we looked at polynomial maps on rings, on usually on commutative rings with identity, and now we take a look at the polynomial maps on groups. So we change to the class of groups. Oh yeah, and before we do this, we I have some good news for you concerning the corona situation. Uh, you don't have to be afraid anymore because I have caught it. I have caught the virus. I found it in our garden. It was hiding behind a bush. And after chasing it for 3 hours, I have it here. I don't let it go out again. So you are safe now. And that's really good news. It's an interesting way to end the pandemic season. Yeah, okay. Excuse me. So if we take the variety of groups, something which is a nice trick there is the following. You take the a group G and so G in the variety of all groups, and then G of X is usually is the set of all elements of the form G sub naught plus C1 times X plus G2 plus C2 times X, and so on, up to set n times X plus G sub n. Now we can transform this a little bit in such a way that we write it, or G1, excuse me, that we write this as G sub naught plus Z1X minus G sub naught. Take this, and then plus, and now we have to add G sub naught again, plus G sub 1 plus Z2X, and then we subtract minus G 1 minus G sub naught. But of course, we have to correct this again in the next term. So the next one would start with G naught plus G1 plus G2 plus Z 3 times X, and then minus minus G2 minus G1 minus G0, and so on. So we see that we can write it in this form, and always you get here some conjugates of Z1X, and so on. And the correction terms G naught plus G naught plus 1, G naught plus G1 plus G2, and so that accumulates. And that's at the end of the story. So we get minus G naught plus G1 plus Gn at the end. And even that Z1 times X can be transformed in another way, in such a way that we write, for instance, G sub naught plus, say, 2 times X minus G sub naught. We can write this as G naught plus X minus G naught plus G naught plus x minus g naught, and use parentheses like this. And if the coefficient of x is negative, of course we had, if we have a minus here, we have a minus here and a minus here, and the rest stays the same. So we see that we can transform all polynomials into a maybe nicer form, namely into a sum of conjugates of x or of minus x. And so we can write it as a sum of elements of the form g sub I plus or minus x minus g sub I. That's another form of these polynomials. And if we take the polynomial functions, then we can write, so p of g is then the set of all sums of these induced polynomial functions. Now these are constant, they remain, and that's the identity, and the map g plus the identity minus g, that's just called an inner automorphism. So it's the sum of all maps g of, excuse me, say g goes to the sum of g I plus or minus x minus g sub I. Oh yeah, and I forgot here to add g sub naught up to g sub n. And we see if the polynomial is zero symmetric, then we had this condition before, then this parenthesis at the end is zero, and we have just this sum here. And the same for polynomial functions. We have to add g sub naught plus g sub n. And so we see that every polynomial map can be regarded as a sum of plus or minus inner automorphisms plus a constant here at the end. And if we take zero symmetric functions, p naught of g, that's the all maps going this way up to here, and without this constant at the end. Now that reminds me of a story when two mathematicians meet for dinner, and they started discussion if the general public knows enough mathematics or not. And one of them is a pessimistic, and the other one is pretty optimistic. So they make a deal at the end of the dinner when they get when the waitress comes with the bill. They will ask the waitress a mathematical question. If she answers it, then the pessimist has to pay for the whole dinner, and conversely. And now the pessimist was pretty sure that he will win, and so he ordered expensive things like lobster or expensive French wines and so on. And after a while, the optimist was concerned that he will have to pay a very, very high bill. So he pretended he had to go to the toilet, and but he went to the waitress and said to her, "When you come with the bill, we'll ask you a question, and please simply answer 1/3 x to the third." "Okay, I can do that," she said. And really, they finished dinner, and the waitress came, and they asked her, "What's the integral of x squared?" And she said, 1/3 x to the third. Okay, that was wonderful. The pessimist had to pay for the dinner, and when George just walked out of the restaurant, the waitress came to the optimist and said, silently to him plus a constant. And so that thing here, we have plus a constant in the case when we do not have a zero symmetric situation. And otherwise, we have this case. And so we say that P naught of G is also sometimes called I of G because it's generated by all inner automorphisms. And we'll return to this type of nearings, a very interesting class later in the course. So that's something for the moment for the polynomial functions on groups. And we might study polynomial functions on expanded groups as well. And here we get, as a surprise, an interesting result in universal algebra. When we were dealing with expanded groups, I forgot one condition. Namely, for all operations, one usually requires this, that for n-area operation, we have the composition or the operation of G1 up to, say, some Gn. We have these operations there, additional to the addition what we have in the group. And we want, if all of those are zero, then the result should also be equal to zero. So nearings qualify this zero composed with zero is zero. And I have to tell you what we think, what we need for expanded groups as when we consider ideals, because we can do this. And the ideal condition would be that we get, of course, a normal subgroup of the additive group. And for all these operations, we get the property that the composition of G1 plus I1 up to G sub n plus I sub n minus the composition of G1 up to Gn must be in the ideal I again. And so you see that's a situation which is very, very similar to the nearing case. And in fact, that was at the first time one didn't know what one really needs for ideals of expanded groups, but nearing theorists knew already we have this condition here, and it must hold for all n-area operations here, and then we get an ideal. It's quite interesting to find out how ideals look like, which are generated by a single element. And we can recall if A is an element of A in some variety V of expanded groups, then if we take the subalgebra generated by A, then we know these are all words over V in the element A. So that's the set of all word functions applied to A all the time, and now word functions just in A. We have only one variable here, where W is in the word algebra over X. So words are the tool which generate subalgebras. And the question is, what are the tools which generates ideals? So the ideal generated by A is given, and the result is quite similar, by the polynomial functions in A, such that P is a polynomial function and a zero-symmetric polynomial function on A. Now, so it's quite interesting. Words generate subalgebras, polynomial functions, I mean zero-symmetric polynomial functions generate ideals in varieties of expanded groups. We'll give examples to that. We'll see examples like that. And let's call it a theorem. And in order to prove it, we have to show that this here is really the ideal generated by A. And so maybe to abbreviate things, let's call this A in these brackets for the moment, so that we have less things to write. First of all, we have to show that A is in bracket A, but A is of course the identity applied to A, and so the identity is a zero-symmetric polynomial function, so this is in bracket A. Next, we show that bracket A is a subgroup, and in fact a normal subgroup. So let's take A and B. That's nonsense. Let's take B and C in bracket A. Then we know that B is some polynomial P bar of A, and C is some polynomial Q bar of A. And now it's easy to see what B plus C is. That's P plus Q bar of A, because that's the way how functions are added. And so we see that B plus C is also an element of bracket A. And the same happens if we take a minus here. And so we have at least that this bracket A is a subgroup. Next step would be to show that it's a normal subgroup. So A is a normal subgroup of A plus. We can do it in this way. Let's take some some B and C in A, and let some D in bracket A, and we have to take care, no, just some B, excuse me. We just have to take care of B plus D minus B's. Now, here we can say we have to have, D will be some P of A, or P bar of A, and these elements here can be considered to be constants. So they are constant polynomial functions. And so that's nothing else than B plus P bar minus B applied to A. And that's again in bracket A. Here I identify the elements of A with a corresponding constant function A, which is a polynomial function, but it's just convenient. Yeah, and finally we have to look at the ideal property. If we take an n-ary operation, and if we take, say, P1 plus P1 bar of A, comma, and so on, P sub n plus P sub n bar of A. And if we subtract the composition of P1 up to P sub n, then we can do the same thing here. We can say this here is nothing else than these are constants, and we form the polynomial of the composition here, P1 plus P1, Pn to Pn, and subtract this. We still get a polynomial function out of this, a polynomial out of this. And if we plug in the value A, we will end in an element generated by A. And so we see that this here is this bracket A is an ideal. It contains A, and it must contain all elements here which are in the ideal generated by A, and hence we it's in the ideal generated by A, and hence it must be the smallest ideal containing A, which is the same as the principal ideal generated by A. That's nice because we now have a description of all elements in the generated ideal in a expanded group, and this goes on. We can do even more. We can look at ideals generated by more elements, because if you have an ideal I which is generated by Z, then this is simply the sum of all ideals small s, principal ideals where S is in S. So if we manage to know what's in the principal ideal, then we see that this is the same, or we can use this for describing generated ideals in general. So let's make a test. What happens if we take groups? If you have a group G out of the variety of all groups, then in an element A in G, the generated subgroup is just a set of all word functions with value A. And what would be the ideal in our case? It's just a normal subgroup, so it's the generated normal subgroup. And you see what we if we take all polynomial functions p bar in p sub naught of G and excuse me, apply it to A, it's the set of all p bar of A, where p bar is a polynomial function and the zero-symmetric one. What do we get? We get, of course, all multiples of A, and also we get, since we have this here, we also get all conjugates of A. If we take the polynomial constant plus x minus constant, and so we get the all multiples and conjugates of A, and that's the familiar form of the normal subgroup generated by A. What about rings? Rings with identity. Well, let's take rings altogether. Let's take a ring R. And we would like to find out what the principal ideal generated by A is. If A is in R, we know from ring theory, this consists of all multiples, integer multiples of A. Then we have all R times A plus all A times R plus all A R A. For those in ring theory, that's a form of the ideal generated by A if it's not, the situation is not commutative. And so we can see that it comes again from zero-symmetric polynomials. Namely, z times x takes care of, if we plug in A, of that part. All R times x take care of that. All x times R take care of this part, and all x times R times x takes care of this. So if we want to have an element in here, we consult the corresponding polynomial here, and the induced polynomial function will give us just elements in here. And you see that's again a zero-symmetric polynomial, and we get the form of all ideals out of that. Note that we do not need x squared here or x to the third. These polynomials here suffice already for describing generated ideals in rings, but it can be more difficult in more abstract situations. Okay, now the next thing is we look at the polynomial function. We take an expanded group again, and we take in algebra from this algebra A, the polynomial functions on A. And since these are functions from A to A, these are they form a nearing, so it's a subnearing of M of A. That's a set of all functions from A to A. And now the question might be, which functions do we get here? Or addressed in another way, which functions from A to A are polynomial functions? And can it be that we have equality here? We might sometimes get this situation. But we make the thing a little more, even more interesting and involved, namely in this way that we say there's something interesting in between here, namely if we change this to C of A, I have to define C of A is the set of all functions f from A to A, such that f is, as it's called, compatible And what does this mean? Compatible means that it brings congruent elements. For every congruence, congruent elements are mapped into congruent elements again, or in the language of expanded groups, we can say it much easier, because here we have the situation that we don't have to deal with congruences, but with ideals, which is much easier. Remember, congruences are a subset of A cross A, while ideals are just subsets of A. So it's much nicer to deal with ideals. And in the case of ideals, it means the following. So if I is an ideal of A, we can say that F is compatible with I if for all the cases where A1 or A is if A, say, if A minus B is in I, that means that A and B differ only by an element of I. And this means that A and B are congruent with respect to I. And this would have to expect that F of A minus B is again in I. And compatible functions are simply functions which are compatible with every ideal. So they respect all congruences, and it means congruent elements here remain congruent after the application of F. And of course, that's a subset in name of A it immediately turns out to be another nearing here in this chain. And we have to take care that P of A is part of C of A, which means that every polynomial function is compatible. And that is pretty easy. So if P bar is a polynomial function, we mentioned, we've seen this last time, that polynomial functions are generated by the identity and all constant functions. So it's P bar is generated by the identity function and all constant ones. And that's about it, because the identity is compatible. As you see here, if A minus B is in I, then if we have the identity function, it's nothing to prove that it's in I. And the constant functions are also compatible, because if A and B are congruent, then we have here constant functions, C minus C, and so we get 0, which is trivially in I. So all the generators for polynomials are compatible, and since the compatible functions form a nearing, it means that also all polynomial functions must be compatible, and so we get this chain here, and P of A is in C of A, and this is in M of A. Maybe do that still. So now a typical question of a mathematician would be, if we have this chain, when do we get equality here? If we start from the point of nearing of polynomial functions here, we might ask, when is P of A already M of A? And then C of A is also clear. It's also M of A. And we call this case that A is polynomially complete if P of A is the same as M of A. So if every function is a polynomial function, which is nice, and we call A to be affine complete, if P of A is the same as C of A. So if the polynomial functions and the compatible functions coincide. The name affine complete comes from the fact that quite often you get affine functions in here, yeah. Now the first thing is especially nice if you can describe every function by every polynomial function. And so we are interested in the case of polynomially complete algebras. And the case of affine complete is also interesting to find out, for instance, in counting polynomials and affine functions or compatible functions and so on. Now let's perhaps do some examples, and perhaps a question, a word. Why uh, do I deal polynomial functions and polynomials in such an extent? And the thing is, in the first lecture, we have seen that the transition from the linear case to a nonlinear case is the transition in the case of rings, from rings to near-rings. And sometimes the full nonlinearity, like in M of A, is too much to handle or too difficult to handle. And so we are sometimes interested in a, say, mild form of nonlinearity. The mild form is not linear, but polynomials are at least easier to handle than arbitrary functions. And so it's a good idea if one wants to explore nonlinearity to start with polynomial functions first. Yeah, let's do some examples. Number one, let's take a finite field in the class of commutative rings with identity are polynomially complete. I abbreviate this by PC for polynomially complete, and that's very easy to see. Take any function on from a finite field into itself, and you would like to take this as a find that this is a polynomial function. Well, it's easy. You can find a polynomial which has exactly the prescribed values at every point by Lagrange interpolation. And since we only have finitely many points at hand in the finite field, the Lagrange interpolation will guarantee that every function can be viewed as a polynomial function. And one can also say a polynomial function of a degree, which is at most the order of this field, as we know from Lagrange interpolation. And so we can be sure that every function from a finite field into itself is in fact a polynomial function. However, if f is an infinite field, then it's not polynomial complete. That's also easy to see. Take a function from f to f, which has infinitely many zeros, but is not zero itself. Then it cannot be a polynomial function because every polynomial function always has only finitely many zeros. And so you cannot reach every function in this sense. We can find out later that the polynomial functions are in some way dense in the nearing of all functions from a field into itself, but not equal. 3. Take still the same RC1 as here. Take f to be the function from the integers to the integers, sending each element z to 1/2 times z squared plus z to the 4th. And this function here turns out to be not a polynomial function, but a compatible function. So this function is compatible, but not a polynomial function. That should be done as exercise. It's question 15 to show that this is the case. So we get an interesting example of, and we see that polynomial functions do not always form the collection of all compatible functions. Turning to groups, so we take a variety of groups. One can see that the group Z2 is polynomially complete. Z4 is affine complete, but not polynomially complete. And if we go one step further, Z sub 8 is not affine complete. So the question arises, which polynomial functions or which groups are polynomially complete and which are not. Now we have one example here for all three cases, and perhaps example of a group which is not 5, still in a variety of groups. We take the group Z2 plus the Hadrol group of order 8. So that's a non-abelian group of order 16. And this group turns out to be affine complete as well, and not polynomially complete. And a good point is number 6. In any variety V, you can say if an algebra A in V is polynomially complete, then A must be simple. That's again easy to see, because if it's polynomially complete, then it must be affine complete. So it must have the property that all functions are compatible. But as soon as we have a non-trivial ideal, not all functions will be compatible. And so the existence of a non-trivial ideal means that there are functions which cannot be compatible. And so we can even say this for affine complete. And so you see that here, excuse me. So here's Z sub 2 is a simple group, and that's the only way to get a polynomially complete group Z sub n. And we have the case already that for rings, we have a complete overview. So question 16 would be to look at R in the variety of commutative rings with identity. and we can say that a ring is polynomially complete if and only if R is a finite field. So you see the case that we get polynomially complete algebras is pretty rare. We are just confined to simple algebras, and sometimes simplicity alone still does not imply PC. So this implication here does not go in the other direction, as we have seen, for instance, for the infinite field that is simple, but it's not polynomially complete. Hence, polynomially completeness is something which is really very special. We know from another area that we have polynomial completeness in the case of Boolean algebras. Boolean algebras are polynomially complete. Every function, also every function in finitely many variables, is a polynomial function, which is the basis of the theory of switching circuits. So I think I can take this. Some more information maybe in 7. What about polynomially complete groups? So we are in the case of groups. G is polynomially complete if and only if we have two situations. Either G is the two-element group, or G is a finite, simple, non-abelian group. So the polynomial complete groups, except C2, are just the famous groups, the finite, simple, non-abelian groups. And this result has many fathers. Some one might say, and we will go to this, it can be shown from the point of nearing theory, as Gerhard Betsch did it many years ago. It can also be proved by other methods, like Lausch and Neubauer had. In any case, it's a highly non-trivial result, and it can only be, well, it needs a rather lengthy proof to find out what's going on here. So that also means that for finite simple non-abelian groups, every function from the group into itself can be nicely described as polynomial function. I told this to some of the big shots in group theory or in simple groups theory, like Aschbacher and so on, and none of them have known this result. And so it's quite nice that one can describe all functions from these famous groups into itself by polynomials. And 8, all affine complete abelian groups are those of the form set P to the A cross set P to the A cross set P to the B cross set P to the C, and so on. where A is bigger than B, bigger or equal to C, and so on. And this is an interesting result. Yeah, and here plus direct products. For different primes P. So you see that what you need here is for affine completeness that you have P to the A twice here and exactly twice. And then C to the P of smaller powers, which can come later on. It's a rather strange result here, and it comes from Carly and Eichinger. So this describes all affine complete abelian groups. The affine complete non-abelian groups are much, much harder, and it's not easy to find them. The smallest one is the C2 times the dihedral group, which I mentioned before, but it's really not so easy. Maybe a result about rings. At least the compatible functions over the integers. Which functions from the integers into the integers are compatible? That's all functions f from z to z, such that f have an interesting form. They are sums of c sub I, a sub I times x minus 1 over I, such that these are integers and the a sub i's are just the least common multiple of 1 to up to I. Very strange. And of course, x minus 1 over I has the usual meaning, x minus 1 times x minus 2 and so on, as many factors as we have in I. And this was found by Weber. And maybe another final result on this is about the polynomial functions on Z sub p to the k. How do they look like? We've seen that the set 4 and set 8 were not polynomially complete, so we have it would be nice to have a characterization, and they are of the form, well, of the form, we don't know the form, but we know the number. The number is given by p to the k times n minus n plus 1 minus s. And I have to explain this. N is the largest integer which such that k does not divide n factorials, and S is the exponent of P in the product of I factorials, I going from 2 to n, capital N. That's result by Keller and Olsen. And one might add that if we have two different primes, P and Q, to the K1 and K2, then this number of polynomial functions simply multiply. So this cardinality is a multiplicative function, and this means that we can find out what the number of polynomial functions are from Zn to Zn. So maybe that's a nice question number 17. Find the number of polynomial functions over Z12. How many functions are polynomial functions? So that's about polynomial completeness, affine completeness, at least for the moment. And we might start with another section for polynomial functions, namely, we go back to the origin of algebra, which was concerned with equations. So we go back to equations and we'd like to find out what an equation is. And we again will find that usually the notation is at least very doubtful and dangerous. So if I write down an equation like in high school, say 2x squared minus 7x plus 5 is equal to x plus 14, we might ask, what does this mean? What is x? And we run again into the same problem. Is x an indeterminate or a variable or a symbol or something obscure? And what means equality here? These two, if we take this as polynomials, they are not equal for sure, because that has degree 2, this has degree 1. And so what's the meaning of this? The best way to do this is the following, that we say an equation. It's just a pair P, Q of polynomials. And so we take the polynomials P and Q to be in the polynomial algebra a v of x. And we can do this with more so-called variables as well. Now, it's not quite common to take an equation of this type. But on the other hand, it's really that's a well-defined notation, and there's nothing doubtful as this equality sign here. And we say, of course, that A in capital A from here is a solution of this equation PQ if and only if P bar of A is the same as Q bar of A. Yeah, that's fine. And now we have everything well defined, and we're quite happy to know what an equation is. We can make things a little easier if we have expanded groups. Then we can do the following. We can bring the right-hand side to the left-hand side. So we can say P1, P2 can be replaced by P1 minus P2 and 0. In expanded groups, we do have a 0. And so we might simply say an equation here is just a single polynomial. Let's perhaps write it in this way. So an equation is just a polynomial. And then a solution of this equation is in some algebra A is defined if P bar of A is equal to 0. Of course, it's a little non-standard to think of an equation as of a single polynomial, but it's perfectly fine and well defined, and we have no problems with this. Now we want to find out, given a polynomial P, when will P have a solution? That's an old question in algebra, and will make things a little more interesting now. By the following definition. We say that the polynomial P, the equation P, is with a notation as we had before, that P is solvable over A if P has a solution in some algebra B which contains A. So we distinguish between solvable within A and solvable over A. Over A means we have to find, if we can find an extension B, of course B should be in the same variety as A. And that makes things difficult, because how do you know if we can find an extension somewhere else? Let's take it, look at some examples. X squared plus 1 is not solvable in the reals, but over the reals. Because we can find some extension in the variety of commutative rings with identity where this has a solution, and that's, of course, the complex numbers, what we're thinking of. Another example, let's take groups. The group P, the polynomial P minus x plus g plus x. If g is not zero, this is not solvable in any group g unequal to zero. So we'll never find a solution there. And that's question 18 to show this. So now something which is really strange is the following. Example 3. Stay again in the commutative rings with identity. And then we look at the polynomial P 2x plus 1. This is solvable over the integers, but not within the integers, because 2x plus 1 has no equal to 0 has no solution. But we can say it's solvable over the integers, because we easily find an extension, for instance, the rationals, where this has a root, a solution, namely 1/2. Minus 1, excuse me. Otherwise, it would be minus 1/2. But now there comes something very strange. We take an extension of the integers, namely r, namely z cross z2. That's still in the same variety of commutative rings with identity. And we claim that it is not solvable over R. It's not. This is rather strange, because we have now a set and it's solvable over set. But if we take another extension, we make it unsolvable in any extension of R. That's easy to see. Let's take, suppose we have a solution in some P, which contains R. Which means a solution, let's call it B. If this holds, that means that 2 times B minus 1 must be 0, or that 2 times B is equal to 1. But that leads to a disaster, namely we have already pairs here, namely 0, 1, which is the same as 1 times 0, 1. 1 is the same as 2 times b, 0, 1. That's 0. And 2 times b. And 2 times b, because we are in the second component in set 2, is 0. So this is equal to 0, 0. And here we have the contradiction, 0, 1 would be 0, 0. Now that's very strange, because if we start with a set, we have two extensions. One in the rationals where it's solvable, and another, this R, and no other extension of R, there will be a solution. And now there comes an interesting question. Given a polynomial, can you decide in the algebra A where you're living, if there will be another extension B somewhere in the outer space, and where this polynomial will have a solution? And this question seems to be completely hopeless, because we have no really overview of all extensions of an algebra which appear somewhere. But the interesting thing is, yes, we can. We can decide here on Earth if there is an extension where our polynomial will have a solution. So we'll see this next time, and we really can do this, and I can say, read my lips to see that we are in fact able to decide this. So time for today is over. Thank you very much for attending again, and hope to see you again next week. And again, please stay healthy. Have a good week.
Thank you.
Thank you.
Thank you. Goodbye.
Thank you.
Bye.
Thank you.
Thank you very much.